Section 2.4 is called the chain rule. And when we're looking at the chain rule, the basic idea of the chain rule is that we have functions embedded inside of other functions. So one basic one you can kind of think of is having stuff underneath of a radical, right? All of whatever's underneath there, maybe it's a polynomial. Maybe you have x squared plus 2x plus 7. So there's a function already there, and then it's got this extra layer, like Garrett mentioned, having this extra layer on top of it of a radical after that. So we're going to look at functions that have that kind of a variety to them. And when we do that, we have a function inside of a function. It looks like what's on the left-hand side. G of x is inside of f of x. And we're wanting to take the derivative of that whole composite. It's called composite function. So the way that we do that is we take the derivative of the outside. So you see the f prime. And then you see g of x simply rewritten. Okay, it did not change. And then after that, you take the derivative of the g of x function and multiply it. So we're going to do some examples. Okay. So the idea is to look at, and this isn't the only way to think about it, of course, but I tend to look at what's in parentheses. Whatever is in parentheses, or if my calculator would force me to use parentheses if there's not something in the problem, whatever's in the parentheses is my inside. Okay? And if it helps you to think about it, you can almost think about it as sort of being blocked out. So I've got pink stuff, or it's almost a red, raised to a power of 5. So just ignore what I've sort of covered up right now and think about the power of 5. When you have an exponent of 5, how do you take the derivative?
5 goes down, then minus 1.
Okay, sorry, my thing is not wanting to write. Okay, so tell me what I'm going to do.
5 times 2.
5 times 2, so I get 10.
Parentheses, 6 minus.
I'll do that in a second. And then it's to the
5
fourth.
minus 4. I mean 1.
All right, so the power of 5 brings the 5 down and decreases the exponent by 4. That's what that rule said, the power rule. And then what goes inside is whatever it was that was originally inside. Sorry, I was trying to erase. So what is originally inside in this problem is 6 minus x squared. So it stays put as 6 minus x squared. And then after this, I take the derivative, what I covered up in red. Okay, so what is the derivative of 6 minus x squared?
Negative 2x.
Negative 2x. And if we were doing the gateway, we would be done. Okay?
Oh, yeah.
Now, we're not doing the gateway in class today, right? That's Wednesday next week. So we're going to combine the pieces that are on the outside. I can't combine it with the part that's to the power of 4 because it's to the power of 4. All right? Order of operations kind of things. I can't combine those. They're not alike. But I can combine the negative 2x with the 10 at the beginning. So this gives me negative 20x. And then 6 minus x squared to the 4th. And that would be my answer. Yay. We just leave a little 4. What was that?
Is that when we always stop simplifying?
Yep, that's when we would always stop simplifying. Yeah, there's no way to combine anything any further. Multiplying it out would be highly unproductive. There's absolutely nothing useful that would come out of that. So, yeah. A lot of work, right? That's what would come out of that. Okay, any questions on that one? Okay, we're going to take a step further then. This one doesn't really quite look like a chain rule. And in fact, you could use the quotient rule to do it. It would be okay. It wouldn't hurt anything. But I want to show you sometimes how you can use a chain rule to make it a little bit more user-friendly maybe. So where do you see, or where could you see parentheses if you're putting this into your calculator? Around the denominator, right? Sometimes your calculator will try to do division early if you don't put parentheses around everything in the denominator. So the parentheses really are right here. And one way to rewrite this then that would be a little bit more conducive for the chain rule is to rewrite the denominator in the numerator. So x squared plus 3x minus 1. And the exponent would be the power negative 1. So I can't bring each individual piece up into the numerator to the negative 1. That's not correct. But if I take all of it up as a whole, put parentheses around it, and I use all of that to the -1, then that is a correct notation, rewriting notation. And then doesn't it kind of feel like the last problem? I've got something with an exponent. So this is the red part that I was talking about on the last problem. All right, so we're going to do g prime of x. Okay. So we've got all of this stuff that's in red to the -1 power. The -1 is the outside part. So what do I do with the -1? I bring it down to the beginning.
Bring down.
And then what will I have as my new exponent?
-2.
-2. So that is the outside derivative. -1 brought down, or a negative brought down. If you want to put a 1 there, go for it. And then -2 is your exponent. And then the part that's inside, that red part, gets rewritten. Okay? So I still have x squared plus 3x minus 1. We're halfway done, because now I have to actually take the derivative of the part that's in red. So what's the derivative of x squared plus 3x minus 1? 2x plus 3. Gateway, we're done.
Okay.
However, on this one in particular, you see a negative exponent for 1, right? And we've talked about before, the negative exponent is not in the original problem. So everything that's raised to the -2 power, we're going to drop it back down into the denominator. The 2x plus 3 at the end will stay in the numerator, as well as the negative that's at the beginning. So this actually becomes that fraction again that we had. It's -2x. You can. I would. Minus the 3 over x squared plus 3x minus 1 squared. And if you think about the quotient rule, remember the quotient rule we did next time that had ho-ho in the denominator, right? Well, do you see the denominator squared now? Yeah, I mean, we would have gotten that denominator squared had we done it with the quotient rule as well. And the numerator would have simplified to this, but the simplification would have been a little bit messier. Okay.
So, if we have something like this, can we usually just do the chain rule instead of the quotient rule?
You can. This one, the reason the chain rule was so friendly was because the numerator was a simple constant. So yeah, when there's a constant in the numerator, this is usually what I do. If there is something besides a constant in the numerator, it is often less helpful to do it with that rule, because you're going to have the product rule and the chain rule in order to do it. And sometimes just doing the quotient rule is easier. So, okay, the next one takes things up a notch. So if you didn't think I ever did anything complicated in class, you're about to be wrong, because this one's pretty complicated. Okay? All right, this one looks really messy because it's got a square root, and underneath the square root there's division. And within the division there are polynomials. Okay? No matter what you do on this problem, you're going to use more than one rule. You're going to be using the chain rule with the product rule or the chain rule with the quotient rule. Okay? Now, there's a couple of ways you could do this. So let me just sort of mention both of them, and you guys can decide which one we want to do as a class. Either way works. Both ways are correct. It's just different ways of thinking about it. So one way to think about this is to rewrite all of this so that it has an exponent of 1/2. That's one way to do that. So if we do it that way, then the chain rule's on the outside, and then when I take the derivative of the inside, I have to do a quotient rule. Okay? So that's option number 1. And there's more options that I'm even going to tell you, but the two that are most sort of like compelling are the ones I'm going to show you. The other option is that you could do each of the numerator and the denominator separately as a power 1/2. So 3t squared minus 2 to the 1/2 over 2t plus 3 to the 1/2. Okay, so you can either notice that from the beginning, the radicals over the whole thing, so the radicals over each part, right? Or you can even notice it from that sort of second step the first step we did, where we notice we have a power 1/2. Well, the power 1/2 just applies to both pieces. If you think about it from this perspective, you're probably going to end up doing a quotient rule,
Anyway.
right? But then when you do the quotient rule, each of the individual numerator and denominator derivatives will have the chain rule in them. I'll mention the third way, but we're not going to do it. The third way is to take what's in the denominator, like you see it now, and to pull it up to the numerator with a power -1/2. It's also perfectly acceptable. It's just not probably the way that anyone's going to naturally think to do the problem, so I'm not going to go down that road.
Would you do that?
Which of the two, what was that?
Would you like to do that?
I wouldn't do it that way. I would do it the first way. That's what I would do on this particular
Yeah.
one. Do you guys want to try the first one? I think it's the cleanest.
Yep.
So you want to try the first one?
Sure.
Write it down? Okay. So we're not going to do this one right now, although it works. They work just fine. We're going to go with it from the first piece. All right, so we're going to do our derivative, h prime of t. And the first thing we're going to do is we have all of this stuff in red, right? And it's raised to the power 1/2. So what do I do when I have something raised to the power 1/2? Bring the 1/2 down and then subtract. Okay, so this is 1/2. I'll fill in the inside in a minute. And then I have an exponent that's now -1/2. So far, so good? What goes inside the parentheses?
Original function.
The original function, everything I crossed out in red. Okay, so 3t squared minus 2 over 2t plus 3. And then after this, I'm going to have the derivative of the red part, the inside. And that is a quotient rule. So let's see how well you remember the quotient rule from your last couple of days of work. What do you do first with the quotient rule? 2t, the bottom, the whole part that we had talked about, the bottom. Times what? Derivative of the top. So what's the derivative of 3t squared minus 2? 6t. And then we have minus. Then we're going to do it the other order, right? The numerator. What's the numerator? And then times the derivative of the denominator, which is just plain old 2. And all of this is over 2t plus 3 squared. And if you were doing the gateway, you would be done.
Wait, really?
Oh, really? Yeah. You guys are like, man, maybe this gateway is a good thing.
Yeah,
Right?
it's
I'm kind of liking this. All right, we have massive amounts of cleanup to do, however, with the algebra for this problem, for our homework, for quizzes, for tests. All right, so let's see what we can do. The first thing that you might notice is that this is a power of -1/2 with the fraction. Now, I have been saying prior to now that we take that and put it in the denominator. I'm not going to do that on this one. What am I really going to do on this one? We are going to do a square root in a minute, but not yet.
Inverse it. Flip it.
We're going to flip it. Right. A negative exponent means really doing the reciprocal. It's simply that if something's in the numerator, it moves to the denominator, but it also means if something's in the denominator, it moves to the numerator. So we're just going to flip this fraction. For the moment, I'm going to leave it with the power 1/2 because I think it's going to make it a little bit easier for our simplification in a minute just to think about it that way. Now, don't go flipping the 1/2. It is not raised to the negative power, right? It stays. So we're going to have this times. And then now we have 3t squared minus 2. And I'm going to go ahead and write it to the 1/2 like this. And again, I'll show you why it's sort of helpful to think about that in a minute. And then we have 2t plus 3 in my numerator to the 1/2. Okay, my next fraction has a 2t plus 3 squared on bottom. That part I don't want to change. But the numerator I'm definitely going to clean up. So just in order to kind of save us some space and some thinking, I'm going to simplify on the top, and then we'll rewrite what we have as our answer lower. So if I were to distribute the 6t through the 2t plus 3, what I get? 12t squared plus 18t. Okay, on the next piece, I'm supposed to be distributing a 2 through, but it's really like a negative 2 because there's a negative in front as well. So I'm going to distribute this 2 and this negative at the same time through the 3t squared minus 2. So if I take negative 2 times the 3t squared, I get, what was it? Negative 6t squared. And then my sign will change on the second one, so I'll get plus 4. And then we're going to combine like terms, so what are we going to get? What are we going to get?
6t squared plus 18 plus 4.
6t squared plus
18t plus 4.
Okay, so is everybody good with that? Okay, just kind of saved us a little bit of rewriting by putting it there. Okay, it would be wonderful if the 6t squared plus 18t plus 4 factored. I'm just going to tell you right now it's not going to. It's something you should check to make sure that it does or doesn't, but this one doesn't actually simplify. Now, it stands a chance, right? Okay, we had one last time where it didn't stand a chance because we had a 20 at the end and I needed it to factor into something with a 3, and that wasn't going to happen. But the 6 at the beginning factors into 2s and 3s, potentially. The 4 at the end factors potentially into 1s and, into 2s, which I have 2 at the end. But I'm not going to get a factor of 3 at the end. I mean, so that part's not going to work. In a minute, I think it'll clean up a little bit better, and you'll see how that actually even plays out a little bit easier for us to identify that. But for the moment, I do want us to recognize there is a piece that does simplify. Do you see which one it is?
Yes. 2t plus 3.
Yeah, there's a 2t plus 3 here and a 2t plus 3 here. Do I see that?
Yes.
Okay, one's in the numerator, one's in the denominator. Even if they were both in the denominator, it would also still simplify. But they're in there in 2 locations and they're multiplied. So we're going to be able to combine them somehow. Do you remember how you can combine those?
2 minus 1/2.
Right, so we actually can take a look at their exponents. So this exponent is a 1/2 and this exponent is a 2. And we can subtract exponents. Now, Mooney said 2 minus 1/2, and that's fine because 2 minus 1/2 will give me a positive number. It just means the answer would then be on the denominator, right? Because the 2 is the larger value and it's in the denominator. So what is 2 minus 1/2? 3 halves. So this will actually be a 2t plus 3 to the 3 halves, but in the denominator. So right now I have my numerator. Well, you know what? Let me just extend this like this. The numerator has this expression we talked about just a moment ago, 6t squared plus 18t plus 4. The denominator already had the 3t squared minus 2 to the 1/2. And now it will also have the 2t, thank you, 2t plus 3, and it will be to the 3 halves. Okay, there's one more simplification that we can do.
2 on the bottom.
We'll do the radicals in a minute, something before that.
2 on the bottom.
Mm-hmm.
Common denominator at the top.
Okay, I don't think we want the phrase common denominator, but
Just like
there's a common factor,
one factor, yeah.
right? The 2 in the denominator at the beginning, and all of the numerator each have factors of 2 in them because they're all even. So we can actually reduce each of the numerator factors, coefficients by a factor of 2. So all of these can simplify. So I actually have 3t squared plus 9t plus 2 on top. And I have the same 3t squared minus 2 to the 1/2. You know, just let me actually do that since we're in the last step and we're about at the bottom of our page. So we already talked about that being a square root. So this is 3t squared minus 2. Pretend like you can see that looks like squared because I'm running out of space. All right, and then the other one is to the power 3 halves. So it's the square root and then cubed. 2t plus 3 cubed. You could see the 2t plus 3 pulled out, right? And then just the square root of that piece. Either of those are versions that would be okay at this point. Take a look at the numerator, though. You should know, after we factored out that 2, that the numerator can't factor. Because at the very best, we're going to get a 3t plus a 1, a 3t plus a 2, we're not going to get the 2t plus 3, which is the only chance that we have, right? So it won't simplify or factor into something that's the same. Okay, so this is messy. Yeah?
Yep.
Yeah, this was a messy one. You ready for the one that's less messy? Okay, but it has trig, so that's the trade-off.
No.
Oh.
That's the
No.
No, you're going to like it, I promise. Okay, here we go. This is one that does not look like it has a parenthesis anywhere. Where is the parenthesis?
Pi x.
Around the pi x. Okay, so if you were putting this in your calculator, so to speak, it would actually force you to do that. Most calculators would anyway. Maybe not all, but most would. That's the parenthesis. So this piece is the inside. This looks very different than the last three that we did. On all of the last three, it looked like an exponent as the outside piece. This time, the exponent is not the outside piece. There isn't even an exponent in the problem. This time, the outside is sine. So we're going to start with what's on the outside, sine. What's the derivative of sine? Cosine. Fantastic. So we're going to write cosine
Pi x.
of pi x. It's the same inside that we already started with.
Who's pi?
times the derivative of the inside.
Right,
Which is pi.
which is pi.
I was
So the derivative of the inside, which is pi x, is the derivative of that pi x, I should say, is pi. Okay? Yeah.
Would you then multiply the pi?
It's a good question, and the answer is no, because this pi that's on the outside is not multiplied by the inside pi x, it's multiplied by the function cosine. So a better way to write that to make that clear is to put the pi at the front. Pi cosine pi x.
Wait, so we take the derivative
Is
of both of them?
Well, we took the derivative of cosine,
Yeah.
or of sine, and it became cosine, and we rewrote the inside as it was.
Oh, okay.
And then we took the derivative of the pi x inside. Parentheses are probably the absolute worst. No, that's not really true. What we do with parentheses is the absolute worst mathematical convention ever because we use them for so many things. We use them to mean multiplication. Right now we're using them to sort of separate the inside of something and the outside of something. They're highly unhelpful. We use them for interval notation. I mean, like, seriously? Could we not come up with some better options? Evidently not. So we have to be a little bit careful. This right here means inside. It does not mean multiplication. Okay? All right, how about this one? That was it. I told you were going to like it, Christian. See? I was right, wasn't I? That was a pretty good one, yeah. This one's not too bad either. It does have an extra step beyond what the last one did. There are two things here that are actually places where we need parentheses. What's one of them?
3t.
The 3t. That's like the last one, right?
Yeah.
But what thing's going on here that we didn't have going on before?
The squared.
The squared. Now, we have this sort of convention where we put the squared beside the cosine, but what we really mean when we do that is we mean that we have the cosine of that angle 3t, all of that squared. Okay? So here's the catch. 3t is an inside function, but so is the cosine of 3t. Trying to get me a highlighter. Let me see about this. Here we go. Come on. Ha. There's two inside functions. Okay? So one of the things that we do when we do order of operations is we work from the inside out. When we do derivatives, we work from the outside in. Okay? So we're going to start on the outside with the power of 2. That's our beginning point. So what is the derivative when we have a power of 2? To have power rule, the 2 comes down. So we're going to get a 10 in front because the 2 will be multiplied by the 5. And then all of this will decrease the power by 1. So it'll be a 1. I'm going to write it just to remind us, but of course you wouldn't have to write it. And what do I do with the inside part? I leave it. I need to simply rewrite it. So it should simply say cosine of 3t. t. Now I'm ready for the part that's highlighted in blue. Okay? In particular, the cosine part of that. What is the derivative of cosine? Negative sine, right? Negative sine. But it needs to be the negative sine of the same angle it originally had, which is the 3t, right? So this is the derivative of the blue part, the outside part of the blue part. And then we need the derivative of the red part, which is just 3. And on the gateway, we would stop there. Okay, so what do we do when it's not the gateway? Well, there's some pieces of this that clean up quite nicely. The 3 at the end, the 10 at the beginning, those obviously clean up, right? That's 30. There's a negative that's sort of embedded in the middle there that I can move out as well. So that's what we're going to do first. We're going to combine all of those. So I've got a negative 30 at the beginning. So I took care of the 10, the negative, and the 3. The other pieces, I don't have a way to combine them any nicer. You can write them alphabetically, or you can write them, I don't care, it doesn't matter. But you're going to have the cosine of 3t. You don't need the parentheses. If you have them there, it's not going to hurt anything. You don't even really need the parentheses around the 3t. I tend to put them around angles more often than not, but they don't actually have to be there unless there's like addition or subtraction going on.
So you don't care which term you go first?
You could write cosine of 3t or sine of 3t. Right.
Don't even think about it, you'll do it later.
Okay.
Okay.
Lost it now.
How are we doing? It's okay?
You're gonna do another step.
Nope, that's it. That's it.
Let's find the third derivative.
Okay, next one. Some more trig, because trig is fun. Ooh, did I hear groans? I mean, really? Ooh, oh yeah, woohoo! Okay, now where on this is the squared?
On the tile setting.
It's on the angle. If the squared were actually meant to be on the cosine, where would it be located? By the cosine. Yeah, so if it helps you to think about it, in fact, let me do this here. I'll do one step of rewrite just to remind us. This is the 3x, that didn't change. This is minus 5 cosine of pi x squared, like that. So it helps you to sort of think about there being parentheses inside of parentheses, so you can do that. The other thing you could write down if you wanted is you could write down pi squared x squared. I mean, really, you could do that. That's not terribly complicated.
Oh.
Okay. All right, so we've got, if you write it as pi squared x squared, you only have one inside. If you write it with the parentheses doubled like this, you have 2 insides. So do you guys want 1 inside or 2 insides? 1. One's easier. So how about we change this, and we'll write this as pi squared x squared. All right, we're ready to take the derivative. What's the derivative of 3x? 3. And then I have minus the 5. It's a constant multiplier, so he just comes along for the ride. What's the derivative of cosine? Negative sine. Now, if you want to write negative sine, you can, but you have to put a parenthesis. My suggestion would be to simply pull the negative to the front in front of the 5 and change that sign. So it would become positive 5 and then sine. And then I didn't highlight it yet, but there's my red, right? The parenthesis part. So what will I do with that piece next?
2 pi.
No, it's still x or pi
Oh,
squared.
I need to first rewrite it. Pi squared x squared. And then we'll take the derivative. Now, I want you to stop for just a second and write down what you believe the derivative of pi squared x squared is. Don't say anything. Shh. Let everybody have a chance to just think. What's the derivative of pi squared x squared? Okay, what do you guys think the derivative of pi squared x squared is?
2 pi, 2x.
I haven't heard the right answer yet.
2 pi.
No?
2 pi squared. 2 pi squared.
You're close. Oh, Garrett's got it. Say it again louder.
2x.
It is 2 pi squared x. Okay, so let's talk about y. Pi squared is a number.
And x is
Okay? Pi squared's a number. Just like the 5 at the beginning of the sine to cosine, right?
okay.
Pi squared will not change because it's a constant multiplier. So pi squared stays pi squared. If you had a square root of 7 there, it would stay square root of 7, right? If you had e, you remember the number e? It would stay e, all right? So we don't change constants.
So could I write it pi squared 2x?
Yes, you could write it pi squared 2x. And then we have the derivative of the x squared, and the derivative of x squared is 2x. So the 2 at the beginning is coming from the x squared part, and then this is what we have. All right, so the last thing that we will do is we can rewrite this to combine the 2 pi squared x with the 5 at the beginning. So this is 3 plus, so 5 times 2 would be 10 pi squared x sine of pi squared x squared.
That's it.
Yep, that's it. And we're going to stop there for today.
We stop.